Hello guys. Today we'll be recording a lecture session on Julia, and today, as part of our course, we will be looking at abstract algebra today. Specifically, we will be focusing on learning about groups. So I hope maybe the audience knows what a group is. If not, I will link this Wikipedia page and some what do you say, really good videos that explain what a group is. And from that point on, once you understand what a group is, then you can come back to this video and you can what do you say, follow along. So we're going into abstract algebra now. A main object of study is groups, and what we're going to do is, a group is a type of set basically, and what we want to do is we want to define this type of set, and we want to define a subset or a subtype of this set. So we're going to define groups, and we're going to define a subset of groups called cyclic groups, which have a different property that differentiates from the rest. So to begin with, what we do is we click on, a main advantage of Julia is something called multiple dispatch. And what do you say, our ability to define our own data types and data structures, not data structures, our data types and our types of sets. So in abstract algebra, basically what you're doing is you're making new algebraic structures. And to start with these algebraic structures, what you want to do is you want to take a set and you want to define how the set interacts with its own elements, or maybe how it acts and transforms into another element. So our main foundation is always a set. And so if we want to do any sort of mathematical anything at all at it, then you're going to have to find a way to define a set to whatever language you're using. And on top of just defining a set, you're going to have to figure out how to actually apply the rules, whichever rules you've put on top of a set. So for example, there's a structure called groups. Groups are going to have their own rules, which is like, it needs to have an inverse it needs to be associative, it needs to have an identity, and it needs to be algebraically closed. This is just for groups. Similarly, there's another structure called rings, fields. All of these different structures have their own different rules. And all of these structures are at their basis, at their foundations, they're all sets with rules upon those sets. So if you want to start anything, you're going to have to know how to define your set, right? So this is what we're doing here. Julia has a keyword for it, which is called abstract. So you're defining an abstract set over here, which is of type group. Okay, that's the first statement, the first cell. You run this, and you're going to define what a group is. All right. So once that is done, what you're going to do is you're going to define your own data structure. So this is where you define your subset, or this is where you define the lower level in your hierarchy, which is just a type of group called cyclic groups. Okay. So in this, what we do, so cyclic group is basically a group that if you apply the same action over and over, eventually it circles back to the identity element, and then from there you keep on doing the same action. So for example, if you had a group, say, of integers mod, let me just open one here. Let me just type here. So let's say you had a set that is 0, 1, 2. All right. And you said this is a group under the operation mod 3 under addition. Right. So if I add a number 1 to the first element over here, 0, then I'm going to get 1. 1 mod 3 is still 1. Similarly, if I add 1 to 1, then 2 mod 3 is 2. Now if I add 1 to 2, 3 mod which is equal to 3. 3 mod 3 is equal to 0. So it circles back to 0. So similarly, you can keep adding and then keep adding and then keep going back, and it has a cyclic nature. So this is what is called a cyclic group. Okay. I will definitely link that Nietzsche, because it takes a fair amount of Yeah, so with that, we have to define what our this is first just defining what our cyclic group is. Now, what we saw earlier was a cyclic group of order 3 because it is modulo 3. So similarly, we can define any order. So that's why n is over there, so that we can have a cyclic group of order n. Okay. Now, over here, let me explain the terms. Struct is going to define your data type. So struct cyclic group at n gives you a data type called cyclic group element, and that is going to have an order capital N. So this capital N you're going to enter and you're going to decide. So now over here on the right, we have this over here. So this says that your new data type is a subclass or a subset or a subgroup, not a subgroup, a subset of your initial data type, that is groups. Okay. And over here, you're just initializing that it's going to be an integer value, and you're going to end the data type. And that's it. You've defined what a cyclic group is now. Now you're going to have to decide, okay, so we've decided, all we've said is that we have a set, we have a certain type of set, and we just said, okay, this is a subset of the set that we earlier defined. Okay, that's all we've given. We haven't given anything about how the elements of these subsets interact. And we've just said, this set will contain integers. Now we have to go on and define more things. So we have our cyclic group, that is defined as a subset of a group. Now we have to start defining what its group operations are. So this is going to be the rules that tell you how each elements interact with another element. This is where that cyclic part comes in. Okay, so we're going to import our plus operation from base, and what we're going to do is, okay, so the plus operation is specifically defined for cyclic groups as just a normal addition, like 1 plus 1 equal 2, 2 plus 1 equal 3, and then 3 mod 3 is equal to 0, so it goes back. So this is a specific definition of addition, right? This is addition modulo 3 in our old example. So similarly, for different groups, our definition of addition is going to change, or our whatever binary operation we want to use is going to change. So it may change for, say, if you wanted to talk about special Euclidean group of order 3 or just special Euclidean group of order n. So for those who don't know group theory, this basically talks about your symmetries or your isometries in R3 space or 3D real space, and over here this is n-dimensional real space. So with that, all this big comment is only saying that your definition of plus can change or your operator can change, and this cell is supposed to explain to you how you can change the definition as you like, right? So over here we have the function, so we're overloading our plus operation with two data types. Okay, this is a binary operation, so we're going to have A that belongs to our cyclic group element, right? And we're going to take B, which belongs to the same cyclic group element. So basically, every time we have an addition where we take one element from one cyclic element and another cyclic element, then only then we're going to use this definition of plus. Okay, so where we get where capital N is passed as a parameter. Okay, so over here our new value, which is whatever we're calculating as a result, is equal to A ka value plus B ka value, right? Remember that 2 plus 1 in a bracket, and outside you have mod 3. So that's what's happening over here. Percentage n is basically, what did I do? Yeah, percentage n is basically mod n. I didn't even know you could shift stuff like that. And then you return whatever you've calculated and end. That's it. Simple stuff. Okay. Now after running it, it just shows key all is good, just showing 190 methods. I do not know where 190 methods came from. Yeah, so we're gonna just run this once. So we take any two arbitrary elements, right? G1 is one element, G2 is another element. Okay, so this is cyclic group 5. So remember how cyclic group 3 went to 0, 1, 2, 3 and the operation was addition under modulo 3. So wait, let me type that. So yeah, so initially we had 0, 1, 2, and the operation was plus mod 3, right? So this time it's changed and it has become, instead of mod 3, it is always the order of the group. Okay, so generally it's mod n. In this case it's mod 5. Okay, because over here the value of 5 is what's passed as n. Okay, and instead of 0, 1, 2, you have 0, 1, 2, 3, 4. So you have 5 elements in total. So yeah, so if you take any two elements from here and you add them mod 5, then you're going to get an element that lies within this set. Okay, so over here, that's why they've taken 3. See, 3 over here, and they've taken 4, and see 4 over here. Okay, so if we add together, so if we add 3 and 4 together, you get 7, right? What is 7 mod 5? That is just 2, and 2 is over here. So if we evaluate this, we should get 2. Okay, let's check that. Let's escape and let's run it. Cyclic group element not defined. Oh, I didn't run it, that's why. My bad. Yeah, there we go. Now it should work. No method matching. Oh yeah, I didn't run the addition part either. Now it should work. Now it should work. Yeah, there you go. There you go. Yeah, panicked for a second. Anyways, so our problem statement is simple. We're just gonna chuck all of this into a big program instead of just keeping it down here. So yeah, our assignment, I'll go over our assignment. Okay, I do not have time. We have a 15-minute limit. So yeah, I'll just describe what the problem statement is. You can come to the notebook and you can check it out, okay? So assignment 2. Today we'll be just writing down everything we've learned. We're going to define a cyclic group of order n as a Julia type. We're going to use abstract to define our group, and then within group we're going to see, it's written over here. We're going to define an abstract type named group. Then we're going to define a parametric structure named cyclic group element, which is a subtype of a group. And it should be an integer field, single integer field. So that's why we put the int, the value in equal to int. And then we're going to overload our plus function from Julia's base module. So then we're going to define our new version of plus, and it should perform addition according to our rules of how we wanted cyclic group elements to work. Okay. So that's it. I have 2 minutes. I can probably just explain an overview, but I would like you guys to probably do it yourself and compare the code, because it's basically the same thing. It's all of the same things just combined. Yeah, see, it's the same thing, and yeah, it's all of these cells just combined. So even if you cut copy paste all of the different cells, you're gonna get the exact same program. Okay. So with that, let me scroll down a little more. Yes, so this is the part I'm kind of excited about. This is a extra, like, additional material that I'm going to teach in another video. So the next video that I'm going to upload after this is going to link with my other lecture series about picturing quantum processes. And yeah, this is going to be sort of like a cameo episode of both lectures. So I'm gonna start recording that now. I'll see you in the next video.